Next we move to problem number 21. It says a solution was added with 0.25 gram of a solute. It got dissolved in 20 gram of water. The water froze at minus 0.42 degrees Celsius. Find out the molar mass of the solute added. So problem number 21 says a solution was added with 0.25 gram of a solute. It got dissolved in 20 gram of water. The water froze at minus 0.42 degrees Celsius. Find out the molar mass of the solute added. Enthalpy of fusion of ice is given at 0 degrees Celsius is 0.60245 delta H joules per mole. Okay, so given the enthalpy of fusion of ice at 0 degrees Celsius, if we call delta H fusion is 60245 joules per mole. Weight of the solute W2 is 0.25 gram, so if you convert into kg, we get 0.25 times 10 to the minus 3 kg. Weight of the solvent if we say this is W1 is 20 gram, so if we convert again into kg, we get 20 times 10 to the minus 3 kg. Okay. So we need to calculate Kf of water here. Okay, so the Kf of water for water, Kf is RTF square M1 by delta H vaporization. Not this is delta H fusion here, not vaporization. This is fusion process, delta H fusion. Where M1 is the molar mass of the solvent, molar mass of the solvent water, and it is 18 gram per mole. So 18 times 10 to the minus 3 kg mole inverse. That is M1, and TF is 0 degrees Celsius, so 273 Kelvin, and value of R here we need to convert in joule unit because delta H is given in joule unit. So gas constant R is the gas constant. In joule unit the value is 8.314 joules per mole per Kelvin. Now if we substitute everything here, we get Kf is 8.314 and then TF is 273 and then raised to the 2, and then M1 is 18 times 10 to the minus 3 and delta H fusion is 60245 joules per mole. So if we calculate this, we get Kf is 1.82 Kelvin kg mole inverse. So once we got Kf, now we need to calculate M2 from the expression of molality. Okay, so we know if the molar mass of the solute is M2, M2 gram per mole inverse, or M2 suppose, so then M2 is Kf times W2 by W1 times delta T, delta TF here. So delta TF here is 0.42. Okay, so delta TF So depression in freezing point is 0.42 degree Celsius, so you get 0.42 Kelvin. Okay, so this is the value of delta TF. So if we substitute now, so 1.82 is the value of KF and W2 is 0.25 times 10 to the minus 3, and W1 is 20 into 10 to the minus 3, and delta TF is 0.42. So if we do it, we get the value of M2. Value of M2 is 54.46 gram per mole inverse, gram mole inverse. So the molar mass of the solute, therefore the molar mass of the solute is 54.46 gram per moles. Next we move to problem number 22. A solution was added with a solute which then boils at 100.18 degrees Celsius. At what temperature will it freeze? For water, Kb and Kf values are given. So basically we here need to calculate M, molality. Okay. So delta Tb is given. So delta Tb is 100.18 minus 100 degrees Celsius. So we get 0.18 degrees Celsius means 0.18 Kelvin, and Kb is 0.52 Kelvin kg mole inverse. We know delta Tb is Kb times M, where small m is the molality of the solution. So we can calculate M here. So M is delta Tb by Kb. So we get 0.18 by 0.52. So we get the value of M here. So once we get the value of M, we can calculate because same solution is being used. Okay, so again we know delta Tf is Kf times M. Now delta Tf is value of Kf is 1.86 times M is 0.18 by 0.52. So if we do it, we get delta Tf is 0.61 Kelvin. Okay. So therefore at what temperature will it freeze? The temperature at which the solution will freeze is 273 minus 0.61, so we get 272.61 K, or we can write minus 0. Okay, this is the one. Okay, so 0.271.270. Okay, no, this is your 0 point. So it will be a 0.73 and then minus 61. So we get 272.39 K. Okay, or we can write minus 0.61 degrees Celsius. 23, problem number 23 says acetic acid associates in benzene to form two molecules. 1.6 gram of acetic acid added to 100 gram of benzene cause a raise in boiling point by 0.38 degrees Celsius. Calculate the Ventop factor and the degree of dissociation of acetic acid. Kb is given. So, the normal molar mass of the acetic acid, the normal molar mass of the acetic acid is 60 grams mole inverse, and of the observed molar mass of acetic acid is Kb times W2 by W1 times delta Tb. Okay, so if we say this is normal molar mass of acetic acid, if we say this is M2, this is our M2, and this is M2 prime. Okay, so M2 prime is 2.6, value of Kb is 2.6, and then W2 is 1.65 grams, so 1.65 times 10 to the minus 3 in kg unit, in SI unit, and value of W1 is given, so 100 gram means 100 times 10 to the minus 3 in SI unit, and delta Tb is 0.38. Okay, so we get this one is M2 prime is 0.117 kg mole inverse. So, this is 1.7 grams per mole. This is your observed molar mass of acetic acid. So, therefore, normal molar mass by observed molar mass is 60 by 117, so you get close to 50, okay, or 0.5, 50% basically, so 0.5. Now, it says that acetic acid associates in benzene to form two molecules. So, 2 molecules of or 2 moles of CH3COH is in equilibrium with dimer of acetic acid. Okay. So, if we start with 1, then it is 0, then if we degree of association is alpha, then this is 1 minus alpha, so it gives you alpha by 2. Okay. So, here 1 minus alpha is number of undissociated acetic acid, number of moles of unassociated here, unassociated acetic acid, and alpha by 2 is the number of moles of associated acetic acid. Okay. So, total number of moles is 1 minus alpha plus alpha by 2. Okay. So, this gives you, so 60 by 117 is nothing but 1 minus alpha plus alpha by 2. So if we consider this one, so alpha is 0.98. So the degree of association, not dissociation, association of acetic acid. So the Van't factor I is, so I is 0.50 and then this is 0.98. Okay. Okay. So the degree of association of acetic acid is 0.98. Next, problem number 24, it says a 0.5% aqueous solution of KCl freezes at minus 0.27 degrees Celsius. Calculate Van't factor and degree of dissociation of the solute at such concentration. Consider Kf is 1.85 Kelvin kg mole inverse. So M observed molar mass, observed molar mass, this is observed molar mass. Is Kf times W2 by W1 times delta T F here. Okay, so if we now substitute Kf, value of Kf is 1.85 and W2, so if we consider 1 kg of the 1 kg of the solvent, so this is 0.5%, so 0.5 times 10 to the minus 3 kg we get. Okay, and then we get 100 times 10 to the minus 3. This is W1 and delta TF is 0.27 times 0.27. Here we are considering 0.5 gram of KCl is dissolved in 100 gram of water. Because this is 0.5% aqueous solution of KCl. So if we calculate this one, we get 0.0394 kg mole inverse. This is M observed. So we get M observed is 39.4 grams mole inverse, and molar mass of KCl is 39 plus 35.5, so 74.5 grams per mole. Right. Okay, so I is 74.5 by 39.4 gives 1.89. So this is the Van't factor I. This is the Van't factor I. So Van't factor I is calculated molar mass. This is calculated molar mass by observed molar mass. We get 1.89. Now let alpha is the degree of dissociation of solute KCl. So KCl is in equilibrium with K plus Cl minus. So initially we have 1, this is 0, 0, and 1 minus alpha gives alpha and alpha. So total is 1 minus alpha plus alpha plus alpha, so gives you 1 plus alpha. Okay, so therefore I is 1 plus alpha by 1. So, we get 1.89 is 1 plus alpha. So, we get alpha is 1.89 minus 1. So, gives you 0.89. So, therefore, the degree of dissociation of KCl is 0.89. Problem number 27 says, when non-volatile solute is added to a solvent, what is the difference in vapor pressure expressed as a fraction of the original vapor pressure equal to mole fraction of solute in vapor phase, mole fraction of solvent in vapor phase, mole fraction of solute in liquid phase, or mole fraction of solvent in. So, the option C is correct. Okay. So, C is the correct option here. Because the relative lowering of vapor pressure is the vapor pressure expressed as a function of the original vapor pressure. So, using Raoult's law, we can write PA is PA naught times XA. So, PA by PA naught gives mole fraction XA, right. So, this is mole fraction of solute in liquid phase is the correct option. Okay. Since, so therefore, mole fraction of solute in liquid phase is the correct option. Since solute is non-volatile, it cannot be present in the vapor phase. It cannot be present in the vapor phase. Problem number 26 says, what are the properties arising due to varying concentration of solute in a given solvent, irrespective of the nature of the solute with respect to the solvent? Colligative properties, intensive properties, extensive properties, solute properties. So we know that colligative property does not depend on the nature of the solute. Okay, so A is the correct option. So the correct option is A. Problem number 27 says, which of the following is Raoult's laws applicable to determine molar mass correctly? Ionic solute in liquid, non-ionic solute in dilute solution, non-ionic solute in concentrated solution, and D is ionic solute. So ionic solid in insoluble form in solvent. So here B is the correct option. B is the correct option, right? So for Raoult's law, in order to calculate the molar mass correctly, so we need to consider non-ionic solute. It should not dissociate in the solvent. So non-ionic solute in dilute solution is the correct answer. So B is the correct option. This is because in order to determine molar masses correctly, it is essential that the solute is non-volatile, non-ionic and present in dilute form as well, and present in dilute form only, means we need to consider dilute solution, present in dilute form only, means dilute solution. If it is ionic, one has to account for its, so we need to calculate Van-Top factors, right, because it will dissociate Van-Top factor. So molar masses can only be calculated from the dilute solution, from the dilute solutions containing non-dissociatable non-ionic solute. Problem number 28 says, which of the following is a colligative property? Relative lowering of fluid pressure, decrease in boiling point, decrease in freezing point, change in volume after mixing. So we know elevation of boiling point is observed, not decreasing boiling point. So C is the correct option. (29) says, which law specifically governs the relative lowering of vapor pressure in solutions? Van-Top's law, Boyle's law, Raoult's law, Amager's law. This is very simple. So this is Raoult's law is the correct. So C is the correct option. Problem number 30 says, which of the following is the best description of a semi-permeable membrane in the context of osmosis? Membrane that allows neither solute nor solvent particles to pass through. Membranes that allows solute particles but not solvent particles to pass through it. Membrane that allows solvent particles but not solute particles to pass through it. Membrane that allows both solute and solvent particles to pass through it. So we know that semi-permeable membrane means only the solvent particles are allowed to pass through, not the solute particles, right? So C is the correct option. So here C is the correct option.